Good morning, everybody.
Good morning.
Good morning.
Morning.
Good morning.
Morning.
Good morning, Julia.
Good morning, everyone. Good morning to your team, dear selection committee. How are you?
Very well. Another great day.
We'll see the participants now. Everyone is very excited about the start of today. Можна, щоб було видно їх, а не мене? Не видно так мені камери. Можна, щоб було видно їх, мене? Не видно їх. You can see them. They are worried, excited, anxious at times, but I think we are turning in a good community now. After yesterday's activities in here, outside the institute, everyone is closer now, more relaxed, hopefully. We will see after the first presentation how they feel when they know which questions you ask. Mars, you wanted to present something?
Yes, and you may comment, dear Julia.
This is the photo from the Monday evening when the majority of the participants arrived. We had a nice dinner together. We first met. Everyone was still a bit stiff, but already getting to know each other. And this is from yesterday. We were taken to some historical sites, to the area of the capital of the Old Kingdom, which to the town that dates back to the 10th century. Was very interesting. The tour was interesting for everyone, for the locals and for the participants from other side of the country, from other cities. You see, we walked around, asked a lot of questions, historical questions. Our dear Taras Kepeshchuk from the Institute was with us. He was, I don't know, helping or asking even more questions of the guide. So we know a lot of history. This is at the remnants of the old castle. This is what survived. Here is we were at the church, old church premise, one of the oldest churches left in the country from the old times, dates, I don't know, 1,000 years back. This is the folk park, you can say, was the expositions of how people lived hundreds years ago. We were trying to play the instrument which people in the mountains used to inform each other. This is like the alarm system of all times. It wasn't so easy. Therefore, you see the efforts that we put. It's called trimbita, the instrument. This was our last, one of the last spots. Because from town to town, from city to city, from region to region, we have different traditions. So it's interesting to get to know each other, to see how we live, how we used to live. This is the dinner. After walking for many hours, 4 or 5 hours of walking, we were ready to have a nice dinner, talk, chat, and relax. This is our trip to the Institute. Every morning, we're in a good mood, getting some sun and ready to work and cooperate. So I hope today will be another day of nice experience. Now with the presentations and new knowledge, new skills, and we will get closer because we are all in one stressful situation here. I think the participants. And we will find a way out. I wish us all a fruitful and nice day, and I'm very thankful to our colleagues from Ivano-Frankivsk to take care of these events, and good luck to the participants.
So let's hand over to the selection committee, as now the competition itself will start, where the selection committee will pay attention to all the presentations, and you will evaluate the presentations and decide about the winners tomorrow afternoon. So let's hand over around to the table of the selection committee. Just some maybe words before we start. What is important for you, or some recommendations for the young people, and then I think the first presentation can start. So, dear selection committee members, now the floor is yours.
Well, I just want to say to everyone, don't be nervous. So I think all the work we have seen from all the papers are very good. So just do your best presentation, and we are here just to observe, and I'm really think that it will be a very nice session from everyone. So just enjoy also what you are doing. Don't be so nervous. We are just very enthusiastic also about this activity. So I just wish you all for all of you that everything goes according to what your expectations.
Yeah, I would just like to second that. I don't think there's much reason to be nervous. It's just, we hope that this is an enjoyable activity for all who are participating. It looks like you're already having quite a bit of fun, and that's really nice to see. We wish we could have been there with you. Frankly, for my own self, I'm just looking forward to your presentations.
You wanted to microphone?
And good luck for all of you.
So Agne and Kang Jung, some opening words from you.
It's good to see you all here, even though it is online. Good luck to all of you, and I believe you are the future of our metrology. Thank you.
I just want to say good luck and just be free and present what you are doing. You know what you're doing, and we do not know really what you're doing. So just present freely, and that's all. Great success.
Thank you very much. We're having a little electricity trouble here with the generator hiccuping, but we can hear you. We're here, all connected. You see everything well.
Actually, yesterday there was an electricity cut in the morning, and we didn't feel it as the generator switched on.
It depends on what appliances are switched on, the equipment, how much, energy is used, but it's working as long as we're not disconnected. It's just that the projector and well, the computer are hiccuping a little bit. I can see you all well, but here at the screen is a bit. You see.
Now it's switched on.
Now it's on, and now it's off. Okay, just a minute or two. I think that we can set it up, I hope. Anyway, the participants can see it on my laptop. You can use my laptop with no problem, and they can see, because they're worried that they will not see their presentations. But as long as my computer works and they can see the presentation here. I'm very sorry. This was unexpected. So I suggest Okay. All right, so I think we are ready. It's stabilized. We can continue now. I'm very sorry for the hiccup, but it wasn't so bad. Thank you very much for your kind words. I think they smiled and breathed out a little bit. I explained that we are all their friends and colleagues, and we're here to support them. And this is the boost. Not nobody wants to somehow press on them or stress them out. So, Moritz, what do you say?
Well, if the equipment is working, then we can start, or we should wait.
Let me ask the IT. Okay. You can see our first brave participant who's ready to present despite any electricity problems or whatever technical hiccups. Andriy, he's opening our presentation day. I'd like to give him the floor and the microphone.
Thank you. Okay. Tak vlastně. Já não sei, mas problem with the tree. Okay. Good morning. My name is Andriy Barchuk, and now I would like to show and tell how our institute provides metrological traceability in Ukraine and what part I play in this process. Metrological traceability is an important aspect of measurement as one of the best ways to assess the uncertainty of a device's measurement is by evaluating its accuracy. This concept becomes significant during calibration, conformity assessment, verification of measurement instruments, and plays a crucial role in participating in international trades. So our efforts are aimed at supporting the energy independence of Ukraine, primarily by maintaining the national reference base, which is state-owned and contributes to state budget revenues, while also creating jobs in Ukraine. Since our NMI works with both governmental and private organizations, the majority of our funds are allocated to maintaining the national reference base. The metrological traceability provided by the state enterprise Ivano-Frankivsk standard metrology can be represented in the form of scheme. At the level of the national state primary standard, there is state primary standard of volume and gas flow rate units DATU, designed for the storage and transmission of volume and gas rate units. This standard has the highest metrological characteristics in the field of the measurement with a total standard uncertainty of 0.1%. Rotary type delta S flow, turbine type TZ fluxy, and drum type EP2. Working standards are located at the transfer standards level. They are used for transporting and transferring volume and gas flow rate units from higher level to lower levels. Our transfer standards cover the budget range from 0.01 to 6,500 cubic meters per hour. The expanded uncertainty of gas volume measurement does not exceed 0.12%. For notebook. At the level of secondary standards, the national DATU M04 and DATU M05, which receive and compare units with the primary standard using methods and means that vary depending on the magnitude of gas flow rate. The expanded uncertainty of gas volume measurement does not exceed 0.15%. Within the flow range of 0.001 to 7,800 cubic meters per hour. In fact, every major industrial firm has a corresponding quantity of measuring instruments for laboratory and departmental needs. It's difficult to imagine that all these measuring instruments are directly compared with secondary standards. Therefore, such enterprise needs to have their own standards, which are used for calibration or verification of working measuring instruments. These standards are included in the traceability chain and therefore needs to be calibrated using transfer standards. At the level of working standards, the working standards collaborated with working standards from transfer standards, according to established intercalibration intervals. This calibration is performed to calculate the metrological uncertainty of working standards, including installation inspection and check of the documentation. After that, we start calibration the pressure and temperature sensor. For those, we use thermostat Lauda Eco Gold, which using oil, and for pressure calibrator MC2 or MC5 calibrator Bimex. After the completion of the process, we begin to calculate all the data. All measurement results are recorded in protocols and approved by the appropriate documents, a calibration certificate. By the way, the process of this level is process of my work, I guess, what I'm doing. In the final result, gas flow meters are examined against working standards within the permissible error limits and then transferred to the consumer. So, thanks to the work of experts of our institute, the metrological traceability of gas volume and flow rate units is ensured from the meter used by the consumer to the national standards, which undergo systematic international comparisons and are added into the BIPM database. So this positively impacts the economy and metrological independence of Ukraine. So I thank you for your attention, and I'm glad to hear your question.
Andre, I have a question.
Okay, okay.
At the beginning of the presentation, you start with the SI, and then you come to the national state primary standard. Can you describe the link between the national state primary standard and the international system of units?
Так, я розумію, звідки. Окей, але я думаю, як сказати англійською. Okay, we are an independent institute and we use international comparisons, and we don't use як ми казали, порівняння ці L. Ні. ILCs, yes, we don't use LC, and we our national primary standard can метрологічну одиницю самостійно. Він отримує метрологічну одиницю самостійно. Зберігає. Так. Самостійно. Okay. Our primary standard realize units by itself. Yeah. And use international system C. Yeah, use kilogram, meters. Але питання, як він, звідки він бере, а не що? Чи яке питання? Oh, maybe can you find the question? Maybe I don't understand.
Can we see the first slide again?
Can you? My presentation, yeah.
Okay, next. Yes, here.
I think here.
So here you have the International System of Units and indirect measurements. So where's the is there traceability, or how is the traceability formed of the national standard to the SI system?
Okay.
Elsa, you can correct me if I don't formulate right the question. Or Agner, of course.
Okay. We use standards with CMC, and by using this standard, we can do indirect measurements from national standards primary to system C. This standard is calibrated and have CMC UA.
I think Maurice wants to know, where do you calibrate your primary standards?
Neither. For this, we using standards which a traceability for to system C.
So you are traceable to mass and time, I suppose.
Yes. We yes, cubometer for hour. Yes.
Yes, and so you this traceability to mass and time, these instruments are calibrated in your institute or at other national metrology institutes?
No. It's other institute.
Yes. Which one? That's what was the question.
P2. Oh, P2B. Yeah.
Yes. Yes. So that is the question. So
Okay, I
the
understood.
traceability chain starts not with your national primary standards, but you are traceable to another national metrology institute. So that's where your traceability starts.
Yeah, I understood. Yeah.
Okay.
My traceability starts from system C. Yeah.
And I have a question for you also. So what do you think is the importance of traceability in our everyday lives? In this case, in the meters we have in our home. What do you think why it is important?
I think it's very important because it's my money. In this month I bought a new gas meters for my home. Yeah, and its traceability is important because it's – let's save me more money. Yes.
Or you are confident with the results, so you will pay for what you actually are getting. Yeah.
It's gas meters. So.
Mm-hmm. Okay. Thank you.
Like no, like I'm household user.
Okay. Thank you.
Thank you. Thank you for your question. Thank you for attention.
Unfortunately, as you can see the list, we have Roman Hural second, but he got high fever this morning, and we were unfortunately informed that he will not be able to attend today. We hope that he feels better tomorrow and we can squeeze him in somewhere in the agenda. He was the one that was absent yesterday due to taking the exams to start his PhD. And I don't know whether he was too overwhelmed, but unfortunately he couldn't make it today. So the next one goes, the next participant is Roman, please.
Good morning, everyone. My name is Roman Hushpet. Today, I would like to present to my experience in developing my own micrometer calibration methodology. The work is devoted to the developments of practical recommendation for calibration of micrometers, budgeting and estimations of anesthesia. Of measuring results. The micrometer applies to machinal and digital micrometers in the range from 0 millimeter to 500 millimeters. Calibration of micrometers can be carried out both in the laboratory and at the place or their work. Because there is not standardized calibration method for micrometers, I developed a typical calibration method in accordance with the requirements of ISO 70025. When calibration micrometers, the following operations should be performance. External inspections, testing, determination of the measuring force of micrometer, determination of deviation from flatness and parallelism of measuring surface of micrometers, determination of deviation of micrometers reading. Standards are used for calibration, gauge block set, flat glass plate, instruments for controlling external calibration condition, and dynamometer for determine the force. When calibration, the micrometer should be held by the thermal infusions pads, or if they are not available, with gloves or an insulated gloves. The gauge block should also be handled with gloves or an insulated gloves. Deviation from the flatness of the measuring surface in of micrometers followed by the interface method using a flat glass plate. the glass plate input on the surface to be measured. In this process, the contact is achieved at which the smallest number of interference bands in observed. Deviation from flatness or defined by the number of interference bands. The reading should be made from the edge of measuring surface by 0.5 millimeter from the surface. In pictures, you can see a different case. In the case when a different number of interference band will be observed on both sides of the contact point, the bands are counted on the side where there are more of them. Deviation from the parallelism of the measuring surface micrometer detected using gauge block, the size of which differ from each other by a value equal 1/4 turn the micrometer screw. The gauge block in place between the measuring surface in position 1, 2, 3, 4 at a distance b, as shown in pictures 2. The deviation from the parallelism of the flat measuring surface micrometer for each other of the gauge block in deferment as the largest difference in micrometer readings at 4 position of gauge block. Determination of the deviation micrometers reading is performed at less than 3 points, averagely spaced only along for the micrometer scale by direct comparison with the gauge block. At minimum 10 replaced reading for each calibration point are performed to assess the measurements uncertainty. The micrometer reading made by the same operation users is the same set calibration condition. To build the model equation, we identified the main source of measurements uncertainty. Taking 3 sourcing into consistence, the model will take the following form. The arithmetic mean value of the length read from the micrometer scales in calculate using the form number 2. At each calibration point, the deviation of the micrometer reading is calculated use the formal number 3. The statistical estimate of the standard deviation of the measurement result is calculated by the formula number 4. The expanded measurements uncertainty is calculated by formula number 5. Total standard uncertainty is calculated by form number 6. The uncertainty of the measurements result is assessed by type A. Type A uncertainty of the measurements result and estimated by statistical analysis of the result of repeat observations. Type B uncertainty estimate by non-static method. The by type B uncertainty caused by deviation from the flatness of the micrometer measuring space is calculated by formula number 8. The type B uncertainty caused by deviation from parallelism of the micrometer measuring surface is calculated by formula number 9. The uncertainty of reading due to the discretes of the micrometer is estimated by type B and calibrated B by formula number 10. If the micrometer is equipped with a digital conscience device, the uncertainty of reading due to the discreteness of micrometer is estimated by type B and calculated by formula 11. The standard uncertainty of the gauge block is calculated by formula 12. Type B uncertainty caused by a deviation from a plane parallelism of steel gauge block is calculated by formula 30. The uncertainty of the drift of steel gauge block since the last calibration is accessed by type B and calculated by the formula 14. After analyzation of the uncertainty, we draw up an uncertainty budget table. Consolation, the development of standard micrometer calibration procedure in integer part of answering measurements, uniformity and metrology traceability of calibration result is a basic for developing a calibration methodology in the definition of a model measurements equate and stability budget. Thank you for your attention.
Okay, so I have a question for you, Roman. What is the larger uncertainty component? So what is the factor that most contribute to the overall uncertainty?
Discrete of micrometer. Discrete scale?
The scale?
Yes.
Okay.
Thank you for your presentation. I have one question about your research here. So using the gauge blocks for the calibration of length devices are really well-known approach. So I am wondering what you really did for enhancing or improving the calibration methodology in this topic.
Excellent. Створив модельне рівняння і created the model equations and and components.
And did you see some improvements by using your method and the conventional method? And did you compare how they are different and how they can be differentiated? I mean, in terms of the impact of this research and later on calibration services.
Між порівнянь це рахується. Що? I work with validation methodology and the quiz time for calibration.
And did you have any comparison with other laboratories, or you are just making improvement on your methodology, and you are just what is your role? You are doing any kind of investigation in experiments, or you are just modeling?
Ну, я на практиці yes. Ні. Як відбувається? We can honestly other calibration laboratory comparisons and result is done good. Потім наступне питання. Покращення роботи на we do the improvements to waste of based on comparisons.
Okay, thank you.
Yes. Thank you for questions. Thank you for your attention.
Dear selection, we have now 10 minutes to the break. Shall we ask the participants from the group that was supposed to be after start, or shall we start the break earlier and come back earlier to continue? What do you say?
I think it's better to have another one, or then we start to have too much together.
Yes.
Yeah.
Okay, may I ask someone? Yes, we have Maria Kopcha, who goes next on the list. She will present next. The floor is yours.
Good morning. And so my name is Maria Kopcha, and here you can see my topic, ensuring measurement validity, stability monitoring of sound calibrators according to ISO IEC 17025. Equipment is one of the most crucial resources for measurement. Laboratory equipment consists with measuring standards which we use to calibrate other instruments, as well as the auxiliary equipment which we use, for example, to monitor the environmental conditions. And all this instrument affecting on the our accuracy of the measurements. And calibration of all these instruments are important to ensure the metrological traceability, but it's not enough to ensure the quality of our metrological services. And to assure the quality, we should follow the requirements of these standards. And let's focus our attention on the subclause 7.7, which according to which the validity of the measurement result are ensured by applying various procedures for monitoring the validity of the results. For example, using some statistical method to identify trade, applying various approaches, use reference materials, alternative equipment, etc. Second is the comparison of measurement result with the result of other laboratories. And last but not least, it's analyzing the data obtained and implementing appropriate corrective action. A fundamental aspect of ensuring the validity of our measurement is not just collection of data, but its interpretation and analysis. The equipment and the measurement process for each parameter should be continuously monitored by the worker through the statistical control. And statistical control means that our measurement process is known, stable, and the observed values are sufficient close to the process to the reference values with control limits. Today I will be speaking about sound calibrators. It's a device which we use to adjust our measurement system using sound level meter or microphone. There are two types of such device. First one is piston phone. It's a mechanical device with a cavity and usually two small pistons that are driven by a miniature electric motor. You can see it on figure 1A. They operate at the frequency 250 Hertz and are generally very stable sound source, but also they depend on the ambient pressure. As the second type is so-called feedback calibrator, and it's a common use in acoustical measurements. It contains, you can see it on the figure 1B. It contains sound source, not very precise, but a very stable microphone. And microphone measures the generated pressures, and via feedback circuit adjust this to proper levels. Thus, a principle leads to a very stable sound source, which is independent on the ambient pressure. And those calibrators usually works at frequency 1 kilohertz. And also this principle is used for multi-frequency calibrator, as you can see on the figure 1C. Next. Oh. Next. Okay, the standard which specifies the requirements for sound calibrators and the method of calibration is standard IEC 16942. According to that standard, we have two methods of calibration sound calibrator. First one is microphone method, and second sound calibrator comparison method. In the microphone method, we use calibrated microphone to measure the generated by sound calibrator sound pressure level. In the second method, our sound pressure level generated from the sound calibrator under test is compared with a calibrated sound calibrator. In our laboratory, we used calibration by the microphone method. Here you can see the calibration scheme. According to the standard, we should measure sound pressure level, distortion, and frequency of each sound calibrator. The microphone is with preamplifier is inserted in the sound calibrator or piston phone, and this microphone is connected to the microphone power supply, which is joined to the voltmeter and total distortion and frequency analyzer. So then calibrator is turned on, the parameters is measured, and then calibrator is turned off, the microphone is removed, and this operation is repeated several times. Once we have measured output voltage, we can estimate the sound level pressure using equation 1. Here we can see U, it's average output voltage, ME, it's microphone sensitivity, then static pressure corrections, transmission coefficient between microphone and preamplifier, and effective loading volume corrections, which is taken from the specification to the sound calibrator. Microphone sensitivity is calculated using equation 2, where we have microphone sensitivity taken from calibration certificate and microphone environmental corrections to the reference environmental conditions, which are listed below. Then we should evaluate our uncertainty of our measurement. Here you can see table with quantity, estimate, standard uncertainty, probability distribution, sensitivity coefficient, and uncertainty contributions. First 5 is related with microphone. It's uncertainty of microphone sensitivity, correction, environmental corrections, pressure, temperature, and humidity, and you call it's polarization voltage. The next 3, it's related to the voltage measured on microphone. Here you can see the standard deviation of the measured voltage, the uncertainty of our voltmeters, and key one, it's transmission coefficient between microphone and preamplifier. And the next one is corrections for the ambient pressure and correction for the effective loading volume of the sound calibrator, which is taken also from the specification. Here you can see for those calibrators, it's equal 0. And finally, we have rounding error for our calculations. So when we have calibration results over time, we can evaluate our long-term stability of our equipment using by control chart, which is useful and simply tool to identify our trends and to control our stability. As a central line, according to the control chart approach, is drawn by the moving empirical average. This is calculated using equation 3. The lower and upper control limits are given by multiply of the standard deviations using equation 5. And we have the multiplication factor key 2 and 3 for the first and for the second control level appropriately. So here you finally can see some results of my work. This result for the multi-frequency calibrator Brühl and Kier 4226, which operates on the nominal frequency range from 31.5 Hz to 16 kHz in octave steps. And it has 3 nominal sound pressure levels, 94 decibels, 104, and 114. As we can see from the figure 4, control charts displays the set of points and control limits. So it's easy to see which our points lie in the control limits and which are under, and identify a trends of for our equipment. As we can see here, the first point lies on the first lower limits, whereas the subsequent next lies are distributed around mean value with a small deviation. This first point was measured after we received this calibrator and before we use it in our laboratory. So it may explain why this point is so different from others. And if we analyzing this chart, so we can conclude that our calibrator is stable and we don't need to increase our calibration interval. Here you can see another example. This is also sound calibrator Brühl and Kier, but type 4231, which operates at one nominal frequency 1 kilohertz and has two nominal sound pressure level 94 decibels and 114 decibels. You can see that those values are also distributed around mean values, but the deviation is a bit large, but it's also, if we draw the trend line, so we can see that our equipment is stable. But the last point in this year, it lies near the first upper control limit. So we need to pay attention on the next calibration. So if our results will be in our control limits or no. And as I said earlier, we used microphones to calibrate our sound calibrator. So we need to monitor not only sound calibrator stability, but the microphone sensitivity, which we use. So here you can see two charts for the microphones LS1 and LS2, which we used to calibrate our equipment. And you can also see that all points lie in the control limits. So if we control our stability of our equipment, and if we fulfill another requirements of the ISO 17025, we could be sure that we give to our customers services with a high quality. Thank you for your attention.
If I may, I have one simple question. Your microphone was calibrated by the BNK, or could you please let me know about this readers from the last slide?
Our microphone is calibrated in our national primary standards of the unit of the sound pressure in air, which has SMS lines.
Okay, which means that you're making the in-house calibrations every year to make sure that your microphone is okay.
There's also a reason why we don't increase our calibration interval, but set it 1 year to be sure that our equipment is under statistical control and nothing can go wrong.
Thank you very much. And another question is that do you have any experience about the comparisons with other laboratories in this field?
As long as I'm working here, I didn't participate in comparison. But
thank you. Thank you very much.
Thank you.
Thank you very much for your presentation, Maria. It was very nice. I would like to know one of the applicabilities for this kind of artifact for the real world. Can you explain?
Yes, for example, those for multi-frequency calibrator, we use it to calibrate sound level meters. So it's like our working standard to calibrate other equipment. So it's also important to know that our working standard is stable and that results that we get during calibration of sound level meters are valid.
Okay, thank you.
And what are the main applications of your customers? Do you face it, or do you know it, or just you get these microphones to be calibrated in your laboratory? If you have, of course, experience.
Sorry, I heard, but Oh,
Just in general.
yeah. Yes, our sound level meters and microphones, for example, microphones can be used to calibrate other equipment like sound level meters, and sound level meters can be used in making measurement of noise, for example, on some on some factories.
Okay, thank you.
Thank you. And thank you for your questions. Thank you for your attention again.
Thank you. Thank you very much for the questions. And this was the first section. Now we're going to have a short coffee break, and we will be here according to the schedule at 11:30 Ukrainian time. Does it work for you, 23 minutes, or what shall you say? Yeah. Let's be here according to schedule
Yeah.
in 23 minutes.
Good idea.
Thank you. We will see you soon. Thank you very much for the questions, and thank you participants for the presentations. Now we're back from the coffee break. Everyone shared their impressions and emotions from the first presentations, and the next participants are ready to present now. We will start with Volodymyr Myslitsky, continuing the category 2, the daily work presentation.
So good morning, everyone. My name is Volodymyr Myslitsky, and my topic is validation of non-standardized methods of calibration of measuring instruments. During the calibration of measuring instruments, international, regional, or national standards are used, but in the absence of these standards, calibration laboratory has the right to develop their own non-standardized calibration methods. According to 7.2.2.1 of ICO 17025, calibration laboratory shall validate their non-standardized calibration method. A laboratory should develop an appropriate validation procedure and validate calibration method developed by themselves for measuring instruments that are in operations in these laboratories. The material presented here provides practical recommendations for the development of own validation procedures for non-standardized calibration methods for measuring instruments. The evaluation of calibration method is a trade-off between cost, risk, and technical feasibility. The convergence conditions imply the same calibration method, the use of the same equipment and under the same condition, participation of the same operator, repetition within a short period of time, probably on the same day, and the same regions if used. The indicators of convergence are the standard deviation of the value of the measured value under the convergence conditions and the limit of the convergence of the measurement results. We obtain n values of the measurement value x from a series. Then we calculate the arithmetic mean of the measurement value and the variance of the measurement results using formulas 1 and 2. So the first criterion is the Grubbs criterion. We analyze the data for possible misses according to the Grubbs criterion. To check whether the largest value of the following in ascending order is not an emission of the data set, the Grubbs statistic is calculated by formula 3. In order to check the significance of the smallest observation results, statistics are calculated by formula 4. And here we see 3 options. If the value of the statistic is less than or equal to its 5% critical value, the position under study is recognized as correct. B, if the value of the statistic is greater than its 5% critical value and less than or equal to his 5% critical value, the item under study is called quasi-outlier. And C, if the value of the statistic is greater than its 1% critical value, the item under study is called a statistical outlier. To check whether the 2 largest observations could be outliers, the Grubbs statistic is calculated by formula 5. Accordingly to the 2 smallest observation results, the Grubbs statistic is calculated by formula 6. If there is any errors, false results are excluded, additional measurements are made if necessary, and the data is checked again using the Grubbs criterion. So here we can see the critical values for the Grubbs criterion that are given in ICO 5725 part 2. So the second criterion is the Cohen criterion. For set of standard deviation, standard deviations calculated from the same number of repeated test results, the statistic underlying the Cohen criterion is calculated by formula 7. And here we see the 3 same options that is the same that was for the Grubbs criterion. Yeah. So here we can see the critical values for the Cohen criterion that are given in ICO 5725 part 2. The following conditions must be met to validate a non-standardized calibration method under conditions of the inter-laboratory reproducibility. The same or different if available calibration method. Use of the same or the other equipment under the same condition. Participation of the same or another operator. Calibration on another day. Other regions if used. The indicators of inter-laboratory reproducibility are the standard deviation of measurement result of the measured value, the statistical estimate according to the Fisher criterion obtained under the conditions of inter-laboratory reproducibility, and the limit of the inter-laboratory reproducibility for the measurement results. So here it is the third criterion. The Fisher criterion in terms of inter-laboratory reproducibility is calculated by Formula 7. Where we see S1 is the variance of the measurement results under the condition of inter-laboratory reproducibility of performer 1, and S2 is the of performer 2. Here we can see critical values for the Christian criterion at the significance level P for the numbers of degrees of freedom. The suitability of the calibration method based on the calibration results and the expanded uncertainty of the results is assessed of the compression coefficient K. Confirmation of the suitability of the calibration method is when the condition is met at Formula 9. And here we can see if the calculated value of K is compared to the critical values as follows. When K is less, more, or equal, the method is or equals that 1, the method is suitable and does not require preventive or corrective actions. But if K is more than 1, the method is unsuitable and requires corrective actions. So in conclusions, in accordance with the requirements of ICO 17025, the possibility of using the methods of calibration of measuring instruments developed by calibration laboratory is clearly defined. The laboratory should calibrate their should validate their non-standardized calibration methods in accordance with their validation procedure. And the material here provides practical recommendation for own developed procedures for validation of the developed method of calibration of measuring instruments, which in turn will facilitate the laborious work and expensive work of these metrological units that carry out calibration of measuring instruments. Thank you for your attention. Ready to answer your questions if you have.
Well, I suppose these techniques, hello, and thank you for your presentation. So I would like just to have a question if I suppose these techniques also can be applied for a standardization method where you have some deviations to the method.
Yes, where we have a standard deviation of measurement value.
No, the question was if you have a standardized method, but you
Yes.
have some deviations to the method, so some of the procedure is not exactly the same, this kind of technique can also validate these changes.
Can you repeat your questions, please?
So you have a standardized method,
Yes.
but you did some changes to that procedure so it fits better your laboratory practice. This kind of techniques, statistical techniques, can also use to validate these changes to the method.
No, validate. Yes, we shall validate.
Okay, thank you.
I have a question myself. I'm just curious whether this is something, this method that you describe is something that you've actually applied yourself in a laboratory. Can you give an example if you have done so?
Yes, we apply this method in our laboratory, and we validate some of our non-standardized methods that our laboratory developed.
Like what kind of methods? Can you give me an example of one?
For calibration of micrometer or some manometer, digital thermometers.
Okay, all right, thank you. Mhm.
Thank you for your attention. Thank you for your questions.
Thank you. And now we have our next participants, Alexandra Popova, who will continue with the category number 2.
My name is Alexandra Popova. I want to. Okay. The topic of my work is advanced requirement for non-standardized calibration techniques. Calibration. Наступний слайд. The key requirement calibration is an important factor or ensuring the quality of measurements taken. The key requirement for calibration are appropriate measuring standards, measuring instruments, auxiliary equipment, calibration methods, qualified personnel, and ensuring appropriate conditions for calibration. In many cases, calibration laboratories use non-standardized calibration procedures developed by the laboratories themselves. Typically, these procedures contain the general requirement for calibration range and calibration points. Назад. Не перемикайте, будь ласка. Дякую. Quite often, the range of reproducible values of quantities, which is provided by the standard, is narrower than the range of calibration capabilities. So the expansion of the range is provided by additional measuring instruments. Some manufacturers of calibrated measuring instruments publish recommended methods for checking metrological characteristics of such instruments. These methods contain a list of recommended equipment for calibration, a list of verified calibration points, and calibration characteristics. In this regard, it seems advisable to supplement non-standardized calibration procedures with appropriate additional. At the same time, to increase the productivity of calibration work, it's advisable to supplement developed methods with in structures for commonly used measuring instruments, which is details the operation performed during calibration. Important issue of quality of ensuring quality of calibration are also provision of intermediate checks of calibration equipment and validation of methods. To carry out intermediate checks, reference standards or auxiliary means can be used. The main purpose of the latter is to check the functioning and stability of the standards being tested. When planning intermediate checks, it's important to determine the range of points to be checked, so the checks will concern the most sensitive points from the measurement range. Planning work to validate the calibration methods includes sample selection and identifying points from the measurement range. When choosing a sample for validation, it's advisable to proceed from the need to confirm stated from the calibration capabilities. In addition, the stability of the sample should contribute to the correct determination of the influence of the fact time between measurements. So there is the stability of calibration equipment that is assessed to a large extent. So in the conclusion, make this information together to optimize the work of intermediate checks on cost-benefit coordinate, and based on the fact that validation of each specific method has its own characteristics, it makes sense to include practical solutions for conducting intermediate checks and validation procedure as part of non-standardized calibration methodology. Thank you for attention.
Thank you for your presentation. I have one question. Your topic is trying to make some ways to make calibrations that self-developed measurement equipment in your laboratory?
Yes, of course. We make non-standardized calibration procedures for our equipment and put all of these factors in it included.
Okay, thank you.
I want to ask, what is the difference between your colleague Vladimir presented a validation for non-standardized calibration methods, the topic and your are very similar. So what's the difference between them? Are you doing some kind of investigation similar to like your colleague Vladimir? And what kind of devices do you analyze for using your methodology?
Так, yes, we do the same. We do the same investigation, but I don't do this on my work because I'm young. Work.
I understand, but what's the difference? Maybe you have some kind of
in my work. In my work, I tell you about the all factors you can put in non-standardized calibration procedures, and the Volodymyr speak about only validation.
So you are doing experimental parts?
Yes. Yes, but I don't do validation.
And what kind of technique do you analyze, basically? I mean, what kind of devices do you have for your research, for your investigations? Are you just analyzing in general?
I work with mechanical stopwatchers, and we have the old non-standard Z calibration procedure, and now we are make it more new, interrupt their unnecessary uncertainty assessment. I work with it.
Okay, thank you.
Thank you.
Thank you, Alexandra. Thank you, dear selection committee. Next comes our next participant, Darina Prodan, with her presentation. I'm inviting you, dear Darina.
Hello, my topic, the topic of my work is defibrillator calibration, analysis of stages and uncertainty modeling. My work addresses the issues and importance of defibrillator calibration. It considers the main stages of calibration process. Heart fibrillation is a condition in which individual groups of heart muscle fibers contract asynchronously. Defibrillators are used to provide emergency medical assistance in such case. Confidence in the correct and reliable operation of the defibrillator is established through the calibration of its output parameters. The consequences of using uncalibrated or incorrectly calibrated defibrillators can be very serious. It can lead to serious injuries or even death. Calibration involves the following stages. The first stage is electrocardiography mode check. Defibrillator analyzers are used for data calibration. It simulates different ACG signals, such like normal sinus or arrhythmic waveforms. The defibrillator analyzes them and after that automatically determines if a discharge is needed. The next stages is cardioversion mode check. The cardio defibrillator synchronizes its discharge pulse with heartbeat, and synchronization of defibrillation with heartbeat is an important aspect of safe and effective device use. The main stages of the synchronization process may look roughly like this: ACG monitoring, determining the cardiac cycle phase, R wave, its heartbeat synchronization, delivering the electrical discharge. Next stage, it's independence determination. Impedance is the resistance between electrodes that the defibrillator must overcome to deliver an effective energy discharge. The size of impedance can vary from patient to patient. Accurate impedance measurement ensures effective energy delivered to the heart. The next the next stage is charge accumulation duration. This factor is responsible for the effectiveness of the defibrillator's operations and determines how quickly the device can be used. The energy level is the subject of calibration. That is why the fifth stage is defibrillation mode calibration. I present uncertainty modeling, modeling equation, at its components. These components include the amplitude of defibrillator pulse voltage, the duration of the defibrillator pulse, load resistance, and standard. These components I presented you to Ishikawa diagrams. Also, I presented the components of the measurement uncertainty, such like measurement uncertainty of voltage level, impulse duration measurement, external load resistance, results for standard, measurement uncertainty associated with the drift of the standards, indication during the calibration period, and measurement uncertainty with the unit of the least significant digit of the reference counter. In conclusion, I want to say that calibration defibrillator is a complex process that requires the careful planning and execution. Modeling measurement uncertainty can be a valuable tool for assessing measurement accuracy and identifying potential issues. Thank you for your attention. If you have questions.
Yes, thank you very much for your presentation. I have a question regarding regulation. Is there any regulation regarding this instrument, or it's only a voluntary calibration in Ukraine?
Unfortunately, it's not standardization in our country, and it's a voluntary, like all calibration in our country.
Okay, thank you.
Thank you for your presentation. I have also one question about this modeling. Have you really put them into practice in real situations, or this just modeling is the theory that you are thinking? Because I want to know if you really have that experience. I want to know which is the dominant factor for the uncertainty estimations and calculations, if you can answer that.
I work with medical equipment, and now it's a theory because I wrote the a calibration method, and it's my project that I want to realize in my department, in my work.
Okay, thank you. Thank you very much.
Now I work, I do the verification in department, but in future I want to write the calibration method and validate them and accreditate in our national accreditation
agency.
And do you have many of customers? Do you cover some kind of region, or you are calibrating for all the country these meters? Or you just tested some kind of them and you're trying to write these rules and methodology?
Now it's very important. My department work with medical equipment, and our region and work with hospital and different hospital. Our regional как нет как, по соседству. Yeah, our region is situated in вокруг near front line. That is why it's very important for our hospital, and that is why I choose this term for our conference.
Thank you.
Any question? Thank you.
Thank you very much, dear Dorina. Dear selection committee, it seems that we are well ahead of time. Our participants present very well in their time slots, and the questions do not take so long. The next participant should have been Vladislav Yarina, but he informed us that he cannot come due to some work constraints and the lack of staff. He works on one of the critical institutions. So he couldn't make it. Therefore, I suggest that we start the category number 3 now, and we can actually finish category number 3 now before the lunch, so that we have more time in the afternoon, and then tomorrow we can continue with category number 1, if you don't mind. So next participant, the first one in category number 3 is Serhiy Dohopoli. He's already coming and he's ready to present the new topic, the new category. Please, the floor is yours.
Thank you. Good morning. My name is Sergey Dovgopoli. I am a graduate student Kharkov National University Radioelectronic. My report on problems associated with nanoplastic and about how metrology can help resolve issues related to plastic, microplastic, and nanoplastic, its toxicity and harm in order to take care of future today. In 2021, production of plastic touched 319 million tons worldwide. In Europe, 50% the production is for packaging materials, and even if more than 1/3 is sent to recycling facilities, or 23% is still sent to landfills. Given that most currently used plastic polymer are highly resistant to degradation, this influx of persistent complex material is a risk to human and environmental health. Continuous delayed interaction with the plastic items allows oral, dermal, and inhalation exposure to chemical components, leading to the widespread presence in the human body of chemical associate is plastic. Human exposure to nanoplastic in inevitable through consuming drinking water, owing to their minute size. These nanoplastics can easily infiltrate cells, tissues, and organs, potentially disrupting cellular functional in giving rise to a spectrum of adverse effects. The accurate assessment of their toxicity relies on the quantification of nanoplastic in environmental samples. Metrological of methods for determining the concentration of nanoplastics in water bodies is critical import for ecological monitoring and preservation of a chaotic ecosystem. Nanoplastic has become a serious threat to a chaotic organism and human health. So accurate and reliable methods of its determination in the environmental matter of primary imports is systeming the critical level of nanoplastics in water is complex and depends on many factors, including the types and size of nanoplastics, particles, their properties, and potential environmental and health impacts. Was some scientific studies indicate that even low concentration of nanoplastic chaotic environmentals can have negative concentration for organism and ecosystem. Nanoplastic can be divided into several main types depending of size, shape, and source of origin. A. Nanoparticles. B. Nanospheres. C. Nanobeads. D. Nanofibers. General categories of plastic determination. Nanoplastic enters the environmental through direct emissions and secondary breakdowns. Microplastics determination may generate in increased number of plastic particles by 2 or 3 order of magnitude. Due to their small size and light weights, nanoplastics possess substantial potential for extensive dispersions in natural surroundings. The period of purification of the chaotic environmental will not always be equal to the period of decomposition of plastic. The degradation period of plastic determinism how long to take for the plastic to natural decomposition and the influence of various physical, chemical, or biological process. On the other hand, the period of purificant water from plastic determinism, how much time it takes for the system to cleanse the water from the existing plastic. The formula for uh, calculating the concentration of nanoplastics in water. The formula calculating a water body cleaning period. In this formula, the different decay times for different types of nanoplastics in take into account the contamination rates is calculating separately for each type. The cleaning efficiency depends on the type of nanoplastics and cleaning process. The formula for calculating the level of harmfulness of nanoplastics. Recommendation for establishing standards and regulation bodies on available toxicological data on the effects of nanoplastics on organism and ecosystem. It is important to develop standards and regulations for exhibition level of nanoplastic in different types of water bodies. These standards must take into account potential risk to human health and the state for aquatic ecosystem. Pollution of water bodies is nanoplastic is global problem that does not respect borders. Metrological support for determining the concentration of nanoplastics in water bodies crucial for environmental monitoring is recommended to develop and establish standards for permissible concentration of nanoplastic in water to protect human health and preserve aquatic ecosystem. Thank you for attention.
Thank you for your excellent topic, and I would like to ask how you defined determination methods for such a huge range of stakeholders, persons who are interested in your topic, and what kind of collaborations do you have regarding these stakeholders? Are they just solely, or they are as institutions interested? What kind of relationship do you have with these customers?
It's зараз хвилину. It's так. scientific experiments работа work. И сказать, ну, это экспериментальное, это просто, я сейчас только начинаю заниматься. Да. This is married to theoretical work that are just static. Не все працює. Ну, тут трохи так. Так.
I'm sorry, this is just a small hiccup. We are all stressed out for a second. It may have stressed Serhi. The electricity is switched off.
Do you want to ask more? Все працює. Ні, тут все є.
Dear Agne, would you like to clarify or add or ask something more? Do we have enough answer? Because I don't know whether we have to invite another participant or we're still waiting for Serhi to tell us.
Okay, thank you.
Thank you very much. Дякую.
Thank you very much.
Thank you very much, dear Serhi. Thank you, dear committee, for the questions. Now I invite Denis Kepashchuk, our next participant, to present in the category 3. Can we have a minute or two? I'm sorry very much, like a short 1 or 2 minutes, because our projector hasn't restarted yet because of the power switch again to the generator. And the audience cannot see anything, only the laptop that is now here on the stand. If we could have a minute or two for all the equipment to restart from the generator.
Yes.
It's starting. So a few seconds.
Okay, let's start. My name is Dennis. I would like to share you my presentation named Study of Metrological Characteristics of household gas meters when measuring consumption of gas and gas hydrogen mixtures. What's the next? Можна, будь ласка, перепутати наступне? Oh, yeah, okay. Okay. Until now, fuel extracted from the earth depths had been used for heating and electricity, both in household sectors and industries. However, this fuel can significantly contributes to the greenhouse effect and on our planet. It can lead to warming, global warming and climate crisis. Therefore, currently, hydrogen plays a significant role in solving the problem of finding alternative new sources, as it can lead to fuel decarbonization and sustained reduction of environmental pollution. Hydrogen is a chemical element, the first element of the periodic table. Hydrogen occupies a unique and fundamental position in chemistry and physics. Under standard condition, hydrogen exists as a diametic gas, H2, that is colorless, odorless, and tasteless. A hydrogen atom designed by symbol H consists of a single proton and one electron, rendering in the simplest and lightest element with an atomic number of 1 and an atomic mass of 1.00797 gram per mole. The main characteristics of hydrogen is the lack of smell. Compared to the other gases, it's the lightest and most fire hazardous, very low solubility in liquids. Compared to other carbon fuels, it has high energy density by weight, but very low volume, so it requires special technology for storage. And how hydrogen can be impact of human health. Gaseous hydrogen is flammable, which can cause a fire. Gas-air mixtures are explosive. Hydrogen can be absorbed into the body when inhaled. With a high concentration of hydrogen, oxygen deficiency in the air. High concentration of hydrogen can lead to oxygen deficiency in the environment. Risk of inhalation. Harmful concentration of this gas in the air will be reached very quickly after a leak. When heated, hydrogen can cause strong burning or explosions as it reacts with air, halogens, and oxygen. Okay, let's begin to the main research phases. This research comprised 5 main phases. The first one is the study of tightness of meters. The second one, determination of metrological characteristics of membrane gas meters. Third one, study of the effect and of hydrogen and gas hydrogen mixtures of membrane gas meters. And fourth, determination of metrological characteristics of meters after exposure to hydrogen and mixtures. And the last, comparison of the error results of membrane gas meters before and after experiments with hydrogen mixtures. So phase number 1, study of tightness of meters. The study was conducted as follows. First etap was tightness of membrane meters were checked using an access pressure of 50 kilopascal. Subsequently, in laboratory conditions, individual filling of each meter was conducted to check tightness. And the final stage of the tightness experiments involved determining the impact of hydrogen and mixtures on the materials which the meter are made, and leading to installation of gas meters in common system, as you can see in the picture. According to the developed testing methodology, excess pressure was measured every 24 hours. The figures show the graph of excess pressure measurement in the test line. Blue column represent the excess pressure value after 24 hours after inflation, and red column represent the excess pressure value after daily additional injection of gaseous hydrogen. The pressure drop over 24 hours is determined by the difference in value between the red and the blue columns. The second main phase is determination of metrological characteristics of membrane gas meters. For this procedure were acquired the following equipment. It was a rotary type meter delta, and reference drum type meter EP, a Bluetooth transistor, and fan with the control center. For this procedure, the rotary type delta was measured flow rates of Qmax 0.7 Qmax, 0.5 Qmax, and the drum type meter was measured 0.25 Qmax, 0.1 Qmax, and Q minimum. This table shows the result of metrological characteristics of gas meters. In this work represent 5 of membrane gas meters, and as you can see, I've made couple of tests and go to an arithmetic mean value. They highlighted by the different colors by different meters. Okay. Phase number 3 is a study of the effect of hydrogen and gas hydrogen mixtures. The figures show the laboratory workplace equipped with sensor warming of hydrogen leaks. For determining of metrological characteristics of membrane gas meter were acquired 1 balloon of 100% of hydrogen and 2 balloons with 2 different mixtures. The first one was where hydrogen was 10% and 90% of gas, and then the next mixture was hydrogen 20% and gas 80%. And for this phase, I used a drum type meter EP, and to measure a flow rate 0.25 Qmax and 0.1 Qmax. This table shows the results of error during operation with 100% of hydrogen and the error before experiments and their difference. The same table, but with a mixture when hydrogen was 10% and gas 90%. There are before experiments and their differences. And the same table with the second mixture where hydrogen was 20% and gas 80%. So we have I have the 4 base there. It was similar as the second base. But at that moment, determination of metrological characteristics was measured after the meters were after the experiments with hydrogen and mixtures, and the final base comparison of metrological characteristics before and after the experiments. The tables show the arithmetic mean value at all flow rates before and after the experiments for each membrane of meter. The permissible deviation of result is plus or minus 0.5%, and values that exceed the permissible limits are highlighted in yellow. As shown at least one point of each meters exceeds the permissible limits of plus minus 0.5%. And conclusions. Based on the research of the leak tightness test of the meter when passing gas hydrogen mixtures, it can be considered that extensional tightness of meter under excess pressure is maintained. However, when checking the internal tightness, it was found the membrane type meters do not fully maintain tightness. As there was a daily drop in excess pressure of the gas hydrogen mixture during the tests. And the results of tests with 100% hydrogen and mixtures showed that the error of the meter increased compared to the pre-experiments when accounting for error, and comparing the metrological characteristics before and after the experiments, it can be seen that the results change at least at one flow rate for each meters. And from this, it can be concluded that hydrogen and gas hydrogen mixtures affect the metrological characteristics of household gas meter of membrane type. So thank you. I'm finished right now.
Thank you for your presentation. I have one question, actually two. First is that you use the pure hydrogen gas and also gas mixtures. Where did you get those gas theorems? I mean, you should have the proper traceability to the gas. Second question is that you used the gas flow meter to do your test. So then I believe it is not the same as using the ambient air. I mean, if you're using the hydrogen, it should be taken into consideration of the effect of the hydrogen into your system. So what additional measures did you take on this test, I think? Please, thank you.
Okay, let's first with the second question. If I understand you right, you mean, you asked me, I have the two ethanol meters, standards, yeah. Why I use it to? You question me.
My question is that we normally use the gas meter for the ambient air, but if you're using the hydrogen, I believe there should be additional measures to make it correct. The measurement should be correct. So I am wondering if you took any other measures to make it the measurement correct, was my question about that.
Yeah. We measured our first of all, it was the research, and for doing the research, I used a standard about hydrogen, and we take the meter we using for calculate gas, and all of the standards I used when I calculate it with hydrogen. You know, the main of this work is for compare the results, how their meters how the meters behave with our standards procedure when we check them by air, and how they show the results by hydrogen in the same conditions, in the same space of work.
And what are the critical factors when doing measurements with hydrogen? With mixtures with hydrogen.
Can you repeat, please?
What are the critical factors that you felt were for measuring these kind of mixtures with hydrogen? I mean, in experimental way and for your meters.
I included the error of pressure, temperature before and after meters, and of course the error of velocity. Oh, I'm sorry, no velocity, velocity, humidity, and of course my error. I can also get error, and because of this, when I show my results, there was a couple of results. It can be, it wasn't a fluke. It wasn't be a fluke, because if that was a fluke, it will it was measured in with the good results. So at this point, I presume it was a good result.
And have you felt any impacts on your meters because of hydrogen? Because it makes sense for materials and for structure.
Yes, that was one. Oh, especially for me, yes, I wasn't held in hydrogen. That wasn't a good experiment, and if it means about the meters, yes, it affect, because when there was a first stage, there was a graphic where meters pressure after 24 hours after inflation dropped, not zero, but very low dropped. So it means the tightness is not very good. It was a little bit of leak.
And why did you not try to have a mixture of 30 and 70? Or just 20% is a limit, or just your experimental access was so
Yes.
managed?
Yeah, I understand your question. Because we have because low than 20% of hydrogen, it won't be have a burning effect, and it can be measured.
Okay, and the last one: have you any access to the pipelines for the customers to measure some mixtures, or just for domestic ones?
Question, because I think it's the other research, how our pipes density will be and maintain hydrogen inside. I can't. I think it's the other research.
Okay, thank you.
Okay, thank you.
I have just one final question, if I can. It's very fast. Do you did the uncertainty calculations, and what were the value you obtained?
A certainty. If I can, yeah, if I open the presentation, the предостанній слайд. Предостанній. Yes, this. On this slide, I measure errors. Sorry. Yes. And what's in this table, all the main results.
But did you do any calculations for the uncertainty?
The uncertainty. No, uncertainty I don't measure.
Okay.
I think measure the uncertainty maybe will be in the next stage of the experiments, if it will be.
Okay, because the uncertainty will be also important to check if your errors are within the permissible deviation. So if your uncertainty is too big then this kind of analysis it's difficult. But anyway, I appreciate that you tell me that is in your future activities.
Thank you for your presentation. You said that you use these hydrogen gas mixtures. Do you prepare these mixtures yourself?
No. We just
No?
I'm not sure we bought it, but we have we have deals with other institute who welcome us to their laboratory, and we yes, I moved to the laboratory where hydrogen using, and they give us. They give us, or my bosses bought it. I don't know. I'm just use it.
Okay. And these gas mixtures are calibrated, or you know this?
Can you repeat?
Is this gas mixture calibrated, or?
Oh no.
No.
I'm
so.
Yeah, they're calibrated and certificated because
Certificated. Okay.
Yes, of course they're certificated.
Okay, Frank.
They are made it by others. Yes,
in the laboratory, they are certificated.
Yes.
Another laboratory. Okay, thank you.
No, I watch that cylinders. I watch that, and they are connected to the whole system, and I'm using that. Use that. Okay.
You are only a user, yes?
I'm a performer. Okay.
Thank you very much.
Thank you. Glad to be here. It was excellent experiment. Thank you.
Thank you very much for the questions. It was probably the longest question session of today's presentations, but it was very interesting to everyone. Thank you very much for the questions, and thank you very much, Denise, for being so brave to answer all the questions. So now I invite the participant who is last in the category, but his presentation is not less interesting or important. So here comes Yuri Moroz with the concluding presentation for today in the category 3. Please, you're welcome.
Hello, my name is Yuri, and my topic development and implementation of digital calibration certificates for volume measurement, instrument and gas flow meter at the Scientific Measurement Support Center of the State Enterprise Ivano-Frankivsk Standard Metrology. Digitalization in metrology is of great importance for increasing the accuracy of measurement, control, and quality assurance in various fields of industry and science. This is confirmed by research by a leading foreign metrology institute working on the creation and implementation of digital calibration certificates to ensure digital quality infrastructure in the context of Industry 4.0 development. Digital calibration certificates, it's a modern tool that enable efficient transmission and storage of calibration data in digital format. Also, it's a great opportunity to machine processing. The purpose of the project is the elimination of the human factor in the application of calibration result, development of digital calibration certificates in XML format for volume and gas flow rate unit, then development of software for generating digital calibration certificates for volume and gas flow rate units. And the final is a gradual implementation of digital calibration certificates in calibration laboratories. The XML certificate structure consists of three main parts. It's administrative data, measurement result, and comment. Administrative data contains the general information about calibration object, information about customer, about meter manufacturer, and etc. Measurement result contains all result of measurement, and the comment contains human readable variant of digital calibration certificates. Functional diagram of the application, which have a code name DCC Genius, consists of 6 steps. The first step is when user choose input data method. We have 2 methods. It's import from Excel when a user import part of information from Excel, or a full manual input from keyboard. When user choose input from Excel, we have a second step. It's insert missing data, because Excel certificate didn't have enough information to complete generating a digital calibration certificate in XML format. Third step, it's a merging process when input data insert to template. And the second step, a program create a TXT protocol which contains all inputted information about certificate. And the last one, it's step number 5. It's a generate digital calibration certificate. Operator can choose which format we can want. It's XML, Excel, or PDF. And the next step number 6, but it's not available in current version. It's uploading certificates in the cloud database. In this screen, you can see some tabs of interface of application. A user can start at begin tab where user can choose which type of certificates I want to create. Also, a user can choose import from Excel, or a user can load information from TXT protocol creation area. Next step, it's general information about certificates. Next step, it's a meter information when where user input data about a gas meter. And the next 2 tabs, it's a meter manufacturer information and customer information. And the last one, but very important part, is a measurement result, where operator input all measurement result data. Also, to describe the characteristic of the standard meter, approximation polynomial is used. The calibration certificate of any format to the coefficient of approximation polynomial specified for calculating the conversion factor K of the standard meter for any flow rate value, according to Formula 1. In this GIF, you can see my program create a digital creation certificate. All output file stored in a special folder named its DCC output. In this folder, each certificate receives its own folder name. You can see in this GIF folder 000K1324. It's a number of certificate. And in this folder, we can see a digital calibration certificate in XML format and the TXT protocol. The certificate has a clearly defined name, the certificate number, date, and date and time when which has been created. How it works? I use a tag method. The tag method is a convention and flexible way to create a digital creation certificate, because it's avoid a direct interference with a software operation. To modify the certificate structure, one simply need to make change in the template and specially necessary tag in the operative field. When a user click a generate button, all information from the field stores in a TXT protocol. This part of this protocol you can see in the right corner of slide. And the fragment of XML structure, fragment of template of XML structure, you can see bottom, the part of code which filling a XML template, you can see bottom. To verify the correct operation of the software, the GameMac tool from PTB is used. After loading the XML format certificate onto the platform, go to Preview tab and observe the information entered using the software. And the conclusion, I analyzed the structure of XML template calibration digital certificate from PTB to obtain necessary information for constructing the digital certificate for volume and gas flow rate units. Then I created a project for digital creation certificate for volume and gas flow rate measurement instrument. Then develop a functional diagram to describe the algorithm of software for creating DCC. And then I develop of software for generating digital calibration certificates for volume and gas flow rate units. And the practical result of using developed software for creating a digital calibration certificate is an XML format that has been verified for content and structure within the developed PTB software GimeMac. Thank you for your attention.
I want to ask a brief question. How do you make sure about the data transfer from your meter? And you must arrange a meter somehow, or you have just a meter that is already have some kind of links? Because not you cannot use every meter. You cannot ensure direct data transfer to your computer, to your database.
Currently, we have in which prover statement we have special programs, and this program give a result, and this result we input manually to my program to create a digital calibration certificate.
If I may ask a question, I understand that this is still at a trial stage, so you haven't adopted this in your laboratory yet. You're not producing these digital certificates. What more do you think is needed for you to start actually using this and generating digital certificates?
Of course, it's a digital sign because it's main part of digital calibration certificates. In our country, we have service. We have in our country we have a DIAPITPES tool. It's a tool from a government to add a digital sign to digital document, and we can upload XML certificate to this tool and give a digital signed XML certificate. But in future, I try to implement this feature inside my app for a full automatically XML creation certificate. I now have API, open API, and in future I can try use it to implement a digital sign inside the app.
Thank you.
I also have one simple question. I could figure out that you benchmarked the genemic of PTB. So I'm just wondering if you have really cooperation with PTB on this topic, or you just benchmark it and you analyze it by yourself and you establish your own system.
When I develop a digital calibration certificate. One little mistake in the structure of XML certificate totally broke it, and I use a GMMAC tool, because if in this structure has been a little problem, it is not opened. But if it's open, it's and this no, it's everything right. If XML certificate opened by GMMAC tool.
Thank you.
Thank you for your questions.
Thank you very much. Thank you, dear jury. And I think we have now concluded with the two categories, category number 2 and category number 3. We have finished a little bit ahead of time, so we will have more time in the afternoon to go around the laboratories of the Institute and get to know what the colleagues here do, what they work with. And I suggest that we will continue tomorrow morning with category number 1, because the participants here started worrying that we will switch to category number 1 now. But as it was scheduled for tomorrow morning, I suggest that we go as per the agenda. So I'm thankful to all the participants. I'm thankful to you, dear selection committee, for all your good questions, everything to the point. Everyone seems to be happy and satisfied and relieved. Half of the participants are really relieved because they have already presented their work. We have another group who is still looking forward to present to you the results and their presentations. Therefore, I thank everyone. Thank you, dear Moritz, for joining us. And tomorrow we will have a very important day with a final set of presentations and the results of the winners of the competition.
Any comment from the selection committee for today?
It's been interesting so far. Looking forward to tomorrow.
Yes, very, very interesting. Thank you for all the presenters of today.
Yes.
Thank you very much. So I'm wishing you a nice afternoon, and I'm wishing us a nice afternoon. We're going to the lunch break, and we will discover more of interesting facts of the Ivano-Frankivsk metrology NMI. Thank you, and tomorrow at the same time and the same place, we're here. Thank you very much.
Bye-bye. See you tomorrow.
Thank you, dear
Bye, everybody.
colleagues. Bye.